Hello everyone, today we are going to learn a very important concept in computer science, that is dynamic programming. Under dynamic programming, we'll be discussing over three sections that are recursion, memorization and bottom-up approach. So let's start with recursion. What is recursion? The process in which a function calls itself directly or indirectly is called recursion. In a recursive program, the solution to the base case is provided and the solution of a bigger problem is expressed in the terms of smaller problems. So let us take an example. Uh, we all know how factorials are generated. Basically, factorial 5 is the multiplication of all the numbers from 1 onwards until 5. So basically, factorial 5 is 5 into 4 into 3 into 2 into 1, that is 120. So in the recursion, what we do is basically, let us say we created a function called factorial int fact that takes an integer n and returns the factorial of that integer. So here the bigger problem is basically finding the factorial of a number, but this bigger problem can be expressed in terms of smaller problems. How is it? See, factorial 5 can be written as 5 into factorial of 4. Then factorial 4 can be again disintegrated into two other parts, that is 4 into factorial of 3. Again doing this on and on, what we are doing basically is dividing a bigger problem into smaller problems. So what we are doing is the same function we can call itself again and again inside itself. So in this function, if n is less than or equals to 1, that is the base case we talked about, that is the solution to the base case is provided, that is n is less than or if n is less than or equals to 1, we are returning 1, else we are returning n times the factorial of n minus 1. So in this case, if n is equals to 5, we'll go to return 5 into factorial of 4. Then this function will call itself, and again this integer n will be now replaced by 4. This will go on and on until and unless the base case arrives. If the base case arrives, it will return 1. That is basically factorial 1 is 1. Then it will go onwards and we will see that this is basically 5 into 4 into 3 into 2 into 1, that is 120. So this is recursion. But let us now take another example. I hope everyone is familiar with the concept of Fibonacci numbers. So in this case, let us say we have to find the nth Fibonacci number in the series. So we defined a function Fibonacci of n. If n, see, this is the best case. If n is less than or equals to 1, we are returning the number itself, that is n. And else what we are doing is we are returning Fibonacci of n minus 1 plus Fibonacci of n minus 2. This comes from the definition of Fibonacci series itself, that each number of the series is the sum of its previous two numbers. So what we do is, now let us see all the stack calls, how they are happening into the function. So let us say we call the function for Fibonacci of n equals to 5. So what Fibonacci of n equals to 5 will do is it will call Fibonacci of n minus 1, that is 5 minus 1, 4, and Fibonacci of 5 minus 2, that is f is equals to 3. That is Fibonacci of 5 is calling 4 and 3. Again, each of these numbers will call upon 3 and 2. 3 will call upon 2 into 1 and all. This will go as a whole tree. Now, the common observation here is that the implementation does a lot of repeated work. Basically, we are finding Fibonacci of 3, Fibonacci of 3, Fibonacci of 2, 2 again and again, and that is consuming a lot of computational power. If you go by this approach, the recursive approach, what you will find out is that due to these repeated computations, you won't be able to find Fibonacci of, let's say, a higher number. Let us say suppose 100. It will take a lot of time and it will be a lot of consumption of computational powers. So what is the solution to this problem? What we know is memorization. Now comes the memorization. So what we will do is, rather than computing these repeated values again and again, what we do is basically we save them somewhere, and if the value comes up again during calculation, we'll just call it from the saved value. It is like, suppose let us take the same example of Fibonacci numbers. What we'll do in this case is basically we create in Python, here we are creating a Fibonacci cache called dictionary called Fibonacci cache. So what will we do is, if let us say if n is in Fibonacci cache, we will just return the value of the key, the value of that key. So and otherwise the whole program is same. Basically n equals to 1, you return 1. If n equals to 2, you return 1. And if it is n is greater than 2, you're returning the Fibonacci of n minus 1 and Fibonacci of n minus 2. The difference here comes after this point. What we are doing is we are calculating the value and we are storing it as a value for a key in the Fibonacci cache dictionary for the value of n, and we are returning the value. So what happens is every time you calculate Fibonacci of n, the value is getting stored into the Fibonacci cache dictionary. So how does it help in solving the problem? Basically, we don't have to make the function calls again and again. What we see is if n is already there in Fibonacci cache, we'll directly use the value from the dictionary. We don't need to compute all the recursive solutions. Let us say we are doing for n equals to 5. So if we do n equals to 5, see, since 4 and 3 are not there already in the dictionary, we will compute 5, 4 and 3. After that, again, when you're calling Fibonacci of 4, what is happening is Fibonacci of 4 is calling Fibonacci of 3 and 2. We'll see that Fibonacci of 3 is already stored into the Fibonacci cache dictionary. So rather than computing it again, what we'll do is we'll directly take the value from this dictionary and compute our next value. So this is about memorization. Another approach to solve this problem is basically the bottom-up approach. In this approach, what we do is basically create an array and iterate over the smaller problems. Let us say bottom-up approach, as the name itself suggests, that starting from the bottom and accumulating the answers to the top. In this type of approach, what we do is we define the base case. If n equals to 0, we are returning 0, and we are creating an array of, let us say we have to find the nth Fibonacci number, so we are creating an array of -1 of all the elements of -1s and of length n plus 1. We are initializing the zeroth and the first element of the array as 0 and 1, and now we are iterating over this array to replace these -1s with another value. That value is basically r of I minus 1 plus r of I minus 2. That is the sum of previous two elements. So while iterating, what we'll find is basically r of 2 is basically r of 1 plus r of 0. Again, r of 3 is equals to r of 2 plus r of 1. If we iterate on this for loop, we will find that the nth Fibonacci number is saved at the nth position in the array R. And since we have to find the nth element, we are just returning the rth r of n. Let us now see the actual practical applications of all these concepts. So this is the first function in Python for Fibonacci, and we are finding the nth Fibonacci number. In the first case, we are using just recursion. So let us say we have to find the Fibonacci's 35th number. So we define the function here using recursion. We are returning Fibonacci of n minus 1 plus Fibonacci of n minus 2. Let us run this function. You see, it takes a lot of time to compute Fibonacci of n is equals to 35. It is still running and it is taking a lot of computation power. It is basically calling these functions again and again to calculate the value of Fibonacci 35. So here we got the value. Now let us see how memorization performs. We created a Fibonacci cache dictionary and we are caching these values to the dictionary. Let us run this cell. And now let us see the Fibonacci memorization of 1000. You see how quick it was. This is all because we are storing these saved values into the Fibonacci cache dictionary and using it again so that we don't have to recurse over the function again and again. Now let us go to the bottom-up approach. We are using the same function as defined in the slides. Here we are creating an array and replacing the elements with r is equals to r of I minus 1 plus r of I minus 2. Let us run this function and see how quick it was. So what we see is basically using dynamic programming, like using memorization and bottom-up approach, you can achieve faster solutions rather than using recursion, because here you are using a lot of computational power, and you can see the difference. Actually, just calculating Fibonacci using recursion for n is equals to 35, it was taking this long. Just imagine how long it would take to calculate Fibonacci using recursion method for n is equals to 1000.